a thermodynamic potential is a scalar quantity used to represent the thermodynamic state of a system. So I am talking about thermodynamic potential, and more specifically this is known as thermodynamic potential energy. Normally the energy term is not used, just thermodynamic potential. This way this is called. Okay. So thermodynamic, so first sentence was the definition of this thermodynamic potential, and this is same as the potential energy used in the analysis of or used in the study of mechanics. There you have studied that potential energy is the capacity to do work, and here in thermodynamics these potentials are used, thermodynamic potential or thermodynamic potential energies. Okay, so these are also energy terms. There are so many terms which are, there are so many potential energy terms in thermodynamics. This concept of thermodynamic potential was introduced by Pierre Duhem in 1886, Pierre Duhem, and later Josiah Willard Gibbs, he give the name as fundamental functions to the same thing, that is thermodynamic potentials. Okay, he gave the name fundamental functions. So in 1886 this concept of thermodynamic potential was introduced, and what are those things? Potentials. Internal energy, this is thermodynamic potential. You have heard the name internal energy, represented by capital U, which is defined as capacity to do work plus capacity to release heat. Okay, I am reading out few things from this board which is not visible clearly to you. Everything will appear on the screen, you can see from there. Okay. So first internal energy term is there. This is thermodynamic potential. Then Helmholtz Free Energy. This is also thermodynamic potential. Then comes Gibbs Free Energy. That is also thermodynamic potential. Enthalpy. That is also thermodynamic potential. Again, Landau Potential is there, which is also called Grant Potential. That is also a kind of thermodynamic potential. Then many more potential terms are also there, such as entropy potentials. First let us come to the point of internal energy. You know that internal energy is defined as the energy of the configuration of a thermodynamic system. It is the energy of the configuration, okay, of a thermodynamic system. And internal energy, this is given by this formula, integration of TdS minus PdV plus sigma mu I dni. The formula you can see on the screen, that thing. And here I have written natural variables. Natural variables for internal energy is entropy, volume and Ni. I am not talking about here Ni, mu I, all these things appear in case of chemical reactions. Okay, otherwise not. So I am not talking about here in this lecture anything about mu I or Ni. Okay. Other variables are pressure, volume, temperature, entropy. Okay. Those things I will talk about in this video lecture. So what are the natural variables? Natural variables are those variables which are held constant during the process. Okay, when we are talking about internal energy of a thermodynamic system, that means, and here I have written S and V, that is entropy and volume. So entropy will not change for the given system in that case when internal energy is being defined. and volume also will not change. They will remain constant. They are held constant. Okay, for the definition of internal energy. And it is equal to what? It is equal to capacity to do work plus capacity to release heat. That way internal energy is defined. And next comes Helmholtz Free Energy, which is Helmholtz Free Energy. This is given by U minus Ts, where U is equal to internal energy, T is the temperature, and S is the entropy. So mathematical formula is U minus Ts, and this is defined as capacity to do mechanical work plus capacity to do non-mechanical work. That way Helmholtz Free Energy is defined. Next comes enthalpy. You know the formula for enthalpy. It is well known to every student, that U plus PV means internal energy plus product of pressure and volume. That way enthalpy is defined, and it is equal to it is defined as capacity to do non-mechanical work plus capacity to release heat. And next comes Gibbs Free Energy, which is defined as capacity to do non-mechanical work. Gibbs Free Energy. Okay, this is defined as capacity to do non-mechanical work, which is equal to H minus Ts, and you know that H is equal to U plus PV. That's why I have written here U plus PV. Okay, G is equal to U plus PV minus Ts. So you know the meaning of all these terms, U, PV and Ts. U is internal energy, P is pressure, V is volume, T is temperature, S is entropy. Okay, and next comes Landau or grand potential, which is equal to U minus Ts. Okay, here in this video lecture I am not talking about those natural variables. Yes, natural variable for enthalpy, this is S and P, and natural variable for Gibbs Free Energy is T and P. So once again I want to repeat the same thing, that natural variables are those variables which are held constant. One more thing, here all the thermodynamic potentials are not independent. Any thermodynamic potential can be derived or can be expressed. Any thermodynamic potential can be expressed in the terms of other thermodynamic potentials. In terms of, okay. So there is one concept, there is one thing in mathematics which is known as Legendre transforms or Legendre transformation. In mathematics you will find this thing. By using Legendre transforms, you can derive any thermodynamic potential by using the thermodynamic potential internal energy. So we can conclude this way, that any thermodynamic potential is equivalent to other thermodynamic potentials. And I have already told you that any thermodynamic potential can be written as the combination of other thermodynamic potentials. Okay. That means any thermodynamic potential is dependent upon other thermodynamic potentials. One more thing, external forces such as force due to gravity, okay, that thing, or electrostatic force or electromagnetic force, etc., these are called here in the study of thermodynamics, these are called external forces, and they are used to count or calculate total energy of the system. Say for example, there is one steam engine sitting on the top of the Mount Everest. So total energy of that steam engine which is sitting on the top of the Mount Everest is more than the total energy of the same steam engine at the bottom of the Mariana Trench. Yes, of course, same steam engine, that means same working fluid is there. Inside the steam engine, same working fluid is there. Okay. So here everything, when I am making the comparison, then everything remains same except for the position or location. The first location was top of the Mount Everest and the second location was the bottom of the Mariana Trench. So there is a difference in what? There is a difference in altitude. Difference in height is there. Means from the center of Earth, the distances of the top of the Mount Everest and the bottom of the Mariana Trench are different. And that's why total energies are different. That's why means what? What is the reason? Reason is gravitational force. Because at different heights or different altitudes, gravitational forces are different. You know this thing. Gravitational force depends upon the distance of the object measured from the center of the earth. If distance is more, then gravitational force is less. If distance is less, gravitational force is more. So, when you are talking about total energy of that steam engine, that means total energy of the working fluid inside that steam engine, it is always more than the total energy inside the same steam engine of the working fluid which is located at Mariana Trench. Okay. So total energies are different, but thermodynamic potentials are same. If you do not count all those extra energies which are coming due to the application of the external forces. Okay, so I'll make separate video for the discussion of natural variables. Yes, one more video can be made just for the natural variables which are used in the analysis of these thermodynamic potentials and those Ni, mu I, all those terms. Those terms appear only in case of chemical reactions. Otherwise, they won't appear. One more thing. We know that conservation of energy, according to conservation of energy principle, energy can neither be created nor be destroyed. Means total energy remains constant. So for internal energy, this is thermodynamic potential, for this internal energy, you can apply this theory, conservation of energy principle. But for Helmholtz free energy or Gibbs free energy, you cannot apply this. Here energy is not conserved. Here the concept of total Gibbs free energy for this point is equal to total Gibbs free energy for this point. This way you cannot means I want to say that you cannot use this concept of total energy remaining constant. And considering this we can say that instead of saying Gibbs free energy or the Helmholtz free energy as energies, instead of saying energies, we should say only useful work. This term we should say, because some energies are wasted. Okay, some energies are wasted. That's why we cannot use the concept total energy remains constant. For internal energy this can be used, but for Gibbs free energy or Helmholtz free energy this concept cannot be used. Okay, so it's better to say instead of thermodynamic potential, useful work. This term should be used, but still thermodynamic potential, this term is used, and you should keep in your mind the difference between internal energy and this Gibbs free energy or Helmholtz energy. Okay, so this was all about thermodynamic potentials. Once again I want to repeat the same thing. Thermodynamic potential means thermodynamic potential energy. Okay, So this was all about this topic. So this is the end of this video. Thank you. Thank you for watching this video.